There is a quiet possibility that nearly everything we have measured about the universe is being distorted by where we happen to live. Not because our instruments are flawed, not because our equations are broken, but because Earth may sit inside a structure so vast, so empty, and so unexpected that it bends our understanding of reality before we even begin to observe it. For most of modern cosmology, one assumption has stood almost untouched. On sufficiently large scales, the universe is uniform. Matter may gather into galaxies, clusters, and filaments, but averaged across great enough distances, the cosmos should look roughly the same in every direction. This idea, called the cosmological principle, is the foundation beneath nearly every major model of the universe. It determines how we calculate cosmic expansion, how we interpret dark energy, even how we estimate the age of reality itself. But that assumption begins to fracture if our region of the universe is not typical. Over the past decade, evidence has accumulated for the existence of a colossal under-dense region surrounding the Milky Way, a cosmic void nearly 2 billion light years across, now known as the KBC void. It is not empty in the ordinary sense. Galaxies still exist here, clusters still form, the night sky remains full of stars. But compared to the cosmic average, this region may contain significantly less matter than it should. And that difference may be enough to alter how space itself behaves around us. At first, this sounds like a minor correction, the kind of detail cosmologists refine all the time. But the implications become disturbing almost immediately. If we live inside a large underdense region, gravity here would be weaker than average. With less matter pulling inward, space would expand slightly faster in our local region than it does elsewhere. And if that is true, one of the deepest problems in modern cosmology may not be a mystery at all, but a consequence of where we are measuring from. This problem is called the Hubble tension. When astronomers measure the expansion of the universe using nearby supernovae and local galaxies, they get one answer. The universe appears to expand at about 73 kilometers per second per megaparsec. But when they infer expansion from the cosmic microwave background, light left over from the early universe, they get a lower value, about 67. Both methods are precise, both are independently tested, and both appear correct, but they disagree. That disagreement should not exist. For years, this tension has been treated as possible evidence of unknown physics. Perhaps dark energy evolves over time. Perhaps gravity behaves differently on cosmic scales. Perhaps the standard model of cosmology is incomplete. But there is another possibility. What if the discrepancy is not revealing new physics at all? What if it is revealing local geography? If we sit inside a giant void, then nearby galaxies would appear to recede faster because they are participating not only in cosmic expansion, but also in a subtle outward flow caused by the void itself. We would mistake a local effect for a universal property, and suddenly, what looked like a crisis in physics begins to look like an observational trap. But that raises a more unsettling question. If a structure this large can distort our measurement of expansion, what else might it be affecting? Because once you ask whether our location biases the Hubble constant, it becomes difficult not to ask whether it also biases dark energy, the age of the universe, the growth of structure, perhaps even the assumptions underlying cosmology itself. And this is where the KBC void stops being a curiosity, because the evidence suggesting it exists does not come from a single anomaly. It appears in galaxy counts, in large-scale velocity flows, in baryon acoustic oscillation measurements, in discrepancies that emerge precisely at the scale where the proposed void should end. Multiple independent observations seem to point toward the same uncomfortable possibility. We may not be observing the universe from neutral ground. We may be observing it from inside a distortion we barely understand. And if that is true, the deeper mystery is no longer whether the universe is expanding faster than expected. It is whether our picture of the universe has been subtly wrong from the beginning. Because if the structure surrounding us alters the measurements we use to define reality, then the next question is unavoidable. What happens when the void begins to affect not just expansion, but the force we believe is driving the universe apart? That force is dark energy, the invisible driver believed to be accelerating the expansion of the universe. For decades, cosmologists have treated it as a uniform property of space itself, a constant energy woven into the fabric of reality, acting equally everywhere. This assumption works remarkably well inside standard cosmology. But it depends on one critical condition, that the universe, when averaged across large enough scales, is fundamentally smooth. A giant void challenges that condition, because in an underdense region, dark energy may not simply operate against the backdrop of cosmic expansion. It may become easier to detect precisely because gravity is weaker. In dense regions, matter pulls galaxies in many directions, masking subtle effects. Inside a void, much of that gravitational noise falls away. Galaxies move more cleanly with expansion itself. The void becomes a laboratory where dark energy is exposed. And that creates a strange possibility. What if the reason dark energy appears to have the strength we measure is partly because we are measuring it from inside an unusually empty region? If void expansion is enhanced by reduced gravity, then some portion of what we attribute to dark energy could be entangled with the structure surrounding us. That does not eliminate dark energy, but it raises the possibility that our estimates of its properties are biased. And once that question emerges, a deeper one follows. What if the void is not merely affecting how we measure dark energy? What if dark energy is actively shaping the void? Because cosmic voids do not remain static, they grow. Matter drains from their interiors towards surrounding filaments, while dark energy accelerates the expansion of the empty space within them. In effect, voids may be the regions where dark energy exerts its clearest influence. The emptier a region becomes, the less gravity resists acceleration. Expansion can dominate more completely. Some cosmologists have suggested that studying voids may offer one of the best ways to test whether dark energy is truly constant. If it is constant, voids should evolve in predictable ways. If it changes over time or varies with the environment, voids may preserve that signature in their shape, their growth, even in the motions of galaxies near their boundaries. Suddenly, the KBC void is not just an anomaly to explain. It becomes an instrument, a tool for probing one of the deepest unknowns in physics. But the consequences do not stop there. Because if living in a void affects how we measure expansion, and perhaps influences how we infer dark energy, then it may also affect how matter itself organizes on the largest scales. And this leads to a paradox much harder to ignore. The Milky Way does not float alone in emptiness. It belongs to a vast gravitational structure called Laniakea, a supercluster containing roughly 100,000 galaxies flowing toward a central attractor. At first, this seems contradictory. How can we live inside one of the largest known cosmic voids and at the same time belong to one of the largest known supercluster structures? But this is where the universe becomes stranger. A void is not an empty hole. It is an underdense average. Within that average, filaments still thread through space. Clusters still emerge. Galaxies still gather. Structure exists inside emptiness. And that means two seemingly opposite realities can coexist. We can inhabit a supercluster inside a cosmic desert. And this is more than a conceptual oddity, because the gravitational flows inside Laniakea may help reveal whether the void is real. Galaxies do not simply drift passively. They move in response to surrounding mass. Their velocities carry information about the unseen landscape of gravity. And when astronomers map these motions, something remarkable appears. Large-scale flows suggest matter is moving not only toward massive attractors, but also outward, in patterns consistent with escape from an underdense region. As if the void itself is shaping the motion of galaxies, as if emptiness has structure. And if that is true, then the KBC void is not merely a gap in matter distribution. It is dynamically influencing the architecture of our cosmic neighborhood. But measuring structures this vast requires more than observing galaxy motions. It requires a ruler embedded in the universe itself. And remarkably, such a ruler exists. Not made of matter, not built by observers, but forged in the first moments after the Big Bang. Frozen sound waves from the infant universe, still echoing across cosmic structure today. And those ancient ripples may hold the most independent evidence yet that the void surrounding us is real. Because if even the oldest measurable patterns in the universe begin to agree with the existence of this cosmic emptiness, then the problem may no longer be whether the void exists, but whether its implications reach far beyond anything cosmology has yet accounted for. Those ancient ripples are known as baryon acoustic oscillations, relic patterns left behind when the early universe was still a hot plasma of matter and radiation. Before atoms existed, pressure waves moved through that plasma like sound through air. When the universe cooled and light broke free, those waves froze into a characteristic scale that still appears in how galaxies are distributed. That scale has become one of cosmology's most reliable distance markers. And yet, even this cosmic ruler begins to suggest something is wrong. When astronomers map galaxy distributions in our region and compare them to what baryon acoustic oscillations predict, they find a subtle mismatch. The local structure appears slightly less dense than it should. The signal is small but persistent. And because this method does not depend on supernova brightness or local calibration, it carries unusual weight. It offers independent evidence that the anomaly may be real. But once the void appears not only in galaxy counts and velocity flows, but in a relic pattern dating back to the early universe, the implications shift again. Because now the question is no longer whether local measurements are biased. It becomes whether the void is leaving fingerprints on the oldest light in existence. That light is the cosmic microwave background. For decades, the cosmic microwave background has been treated as the cleanest window into the early universe, a nearly perfect thermal afterglow carrying the imprint of primordial structure. Tiny temperature variations in that radiation have allowed cosmologists to reconstruct the composition, geometry, and evolution of the universe with extraordinary precision. But that light did not reach us through empty nothingness. It crossed the structures that formed over billions of years, including voids. And this matters because light passing through a large expanding void can lose a small amount of energy through a subtle relativistic effect. The process is tiny but measurable. It produces slight temperature deficits in the microwave background. In other words, voids can alter the oldest light we observe. And if a structure as large as the KBC void surrounds us in all directions, its effect may be diffuse, difficult to isolate, but impossible to ignore. Now the problem deepens. Because if the void affects supernova measurements, galaxy flows, baryon acoustic oscillations, and perhaps even the cosmic microwave background, then we are no longer dealing with isolated discrepancies. We are seeing multiple pillars of cosmology bend in the same direction. That should be reassuring, but it is not, because there is another interpretation. If so many independent measurements appear strained, perhaps the problem is not the void. Perhaps the problem is gravity itself. This is where one of the oldest and most dangerous possibilities in modern physics enters the story. What if Einstein is incomplete? General relativity has survived every major test for more than a century. It explains black holes, gravitational lensing, the expansion of space, the dynamics of the cosmos. It is one of the most successful theories ever constructed. And yet, it was never tested directly on scales of billions of light years. It was assumed to hold. There is a difference. Some physicists argue that structures like the KBC void may be difficult to produce not because our location is improbable, but because our theory of gravity underestimates how matter organizes at the larger scales. If gravity behaves even slightly differently in low-density environments, then larger voids, stronger bulk flows, and richer structure could emerge naturally. Suddenly, the void stops looking like an exception. It starts looking like evidence. This is why alternative gravity theories, once considered fringe, have returned to serious discussion. Not because they have replaced standard cosmology, but because the anomalies have become harder to dismiss. And yet, this creates a brutal dilemma. If gravity must be modified, enormous parts of modern cosmology may require revision. But if gravity remains correct, then we may occupy a statistically rare location that biases our observations. Either possibility is unsettling. And then a deeper contradiction appears. Because this debate does not just affect expansion or structure, it reaches into time itself. The age of the universe depends on expansion. Change the expansion history, and you change how old reality is. If the higher local expansion rate is the true cosmic rate, the universe may be younger than the standard estimate of 13.8 billion years. Perhaps significantly younger. But there is a problem. Some stars appear almost as old as that estimate itself. Ancient globular clusters, white dwarfs cooling for billions of years. Metal-poor stars formed near the dawn of galaxy formation. They all point toward a universe old enough to contain them. And now a paradox emerges that cuts deeper than the Hubble tension. If the local expansion rate is correct, some stars may be nearly older than the universe. That should be impossible. Which means something is wrong. Either our measurements of expansion are distorted, or our understanding of stellar evolution is incomplete, or the cosmological model connecting them contains a flaw hidden so deep we have only just begun to glimpse it. And notice what has happened. We began with a possible void. Then expansion was questioned. Then dark energy. Then gravity. Now cosmic age itself. Every attempt to contain the anomaly has made it larger. This is no longer a local puzzle. It is becoming a chain reaction. Because if a void can force us to question the age of the universe, then the next question is almost unavoidable. How many other structures exist that standard cosmology may have underestimated? And what happens if the KBC void is not unusual at all? What happens if it is merely the first example we happen to notice? What happens if it is merely the first example we happen to notice? That question becomes harder to dismiss once astronomers began finding evidence for other structures that seem uncomfortably large. If the KBC void were unique, it might be treated as a statistical accident. Rare things can happen in a universe this vast. But when multiple anomalies begin appearing in different forms, the argument for coincidence starts to weaken. One of the most provocative examples lies far beyond our local region, in a distant, underdense structure associated with one of the strangest features in the cosmic microwave background, a cold spot. For years, this region puzzled cosmologists because its temperature appeared lower than standard models easily predict. At first, it looked like a statistical oddity, perhaps an improbable fluctuation from the early universe. More exotic ideas even emerged, including suggestions that it might reflect physics beyond our universe entirely. But then another possibility appeared. What if the cold spot was not primordial? What if it was local to the path the light traveled? Surveys in that direction revealed evidence for an enormous supervoid. Light from the cosmic microwave background appears to pass through this underdense region before reaching us, losing a small amount of energy as the void expands. Once again, emptiness seemed capable of imprinting itself onto observation. And once again, a void appeared tied to a major cosmological anomaly. This matters for a reason larger than the cold spot itself. Because two giant supervoids are harder to dismiss than one. The statistical problem changes. A rare fluctuation can be tolerated. Repeated rare fluctuations begin to suggest the model generating those probabilities may be incomplete. And now a historical shock begins to emerge. Perhaps the universe has been giving hints for years that large-scale structure forms more violently, more unevenly, more dramatically than standard cosmology has allowed. Consider the pattern: supervoids, superclusters, bulk flows larger than predicted, walls of galaxies stretching across impossible scales. Each anomaly individually can be debated. Together, they begin to look less like exceptions and more like symptoms. This is where the discussion turns from observational puzzles toward a deeper historical possibility that cosmology may have inherited a simplifying assumption that reality never fully obeyed. The assumption of large-scale smoothness may not be wrong in principle, but it may be too idealized, too clean, too dependent on averages hiding structure that matters. And if that assumption weakens, then one of the most uncomfortable ideas in science returns. The cosmological principle itself may be only approximately true, not exact. Approximate. That sounds subtle. It is not. Because nearly every major cosmological inference depends on that principle. Expansion, dark energy, large-scale geometry, even the interpretation of what counts as a typical observer. If the universe is less homogeneous than assumed, many calculations remain useful, but their precision may be overstated. Their certainty may be artificial. And suddenly, the KBC void stops looking like a regional curiosity. It starts looking like a fault line running beneath modern cosmology. But the historical shock deepens further, because some researchers argue the real evidence is not just in structures themselves. It is in motion. Galaxies across hundreds of millions of light years appear to participate in coherent flows larger than simple models predict. Matter does not merely cluster. It streams. It drifts. It responds to gradients larger than expected. And this introduces an unsettling thought. What if the universe is dynamically rougher than we assumed? not just structurally uneven, but in motion itself. If true, then some of our cleanest models of how matter evolved after the Big Bang may require revision. And now the debate becomes dangerous. Because once structure formation is questioned, dark matter enters the argument. Lambda cold dark matter, the standard framework, does not merely explain expansion, it explains how cosmic structure grows. If giant voids and giant flows repeatedly strain those predictions, the tension may not stay confined to one corner of cosmology. It may spread into the model's foundation. And yet, abandoning the model is not simple, because it still explains enormous amounts of data extraordinarily well, which produces a contradiction no one can easily escape. The model works, and the anomalies persist. Both appear true. That is the signature of a scientific crisis. Not failure, but pressure. Pressure where theory and observation begin grinding against one another. Historically, that is often where revolutions begin. Not when old theories collapse outright, but when they continue succeeding while exceptions refuse to disappear. And then another historical shock appears, the Hubble bubble. The idea sounds almost absurd at first, that our measurements of the universe may be reliable only when looking beyond our local region. That nearby observations may be systematically biased by the very structure surrounding us. But if true, this changes something profound. It means distance itself becomes epistemological. How far you look changes what reality appears to be. Inside the bubble, one universe. Outside it, perhaps another. Same cosmos, different inferred laws. That is not just a measurement problem. That borders on a philosophical rupture. Because science assumes observation converges toward truth. But what if location delays that convergence? What if proximity deceives? Then our cosmic maps may be shaped not only by what exists, but by where we stand while trying to see it. And this leads directly into one of the strangest consequences of all. The void does not merely distort measurements. It may limit what structures can form inside it. In dense regions, galaxies collide, merge, build clusters, ignite violent evolution. In voids, much of that never happens. The environment filters possibility. Some structures simply fail to emerge. Reality develops differently depending on where matter begins. That is a startling thought, because it means the universe may not evolve as one universal process, but as multiple environments producing different histories, different cosmic ecologies, different evolutionary pathways. And if that is true, then the KBC void may not merely be affecting our measurements of the universe. It may have shaped the very kind of cosmic neighborhood in which the Milky Way was allowed to form. Which raises a question even more destabilizing than whether cosmology is incomplete. If the structure surrounding us helped shape our galaxy, then how much of what we call our place in the universe has been determined by the void itself? And if that is true, the consequences are no longer merely observational. They become existential. Because once the void is no longer just a distortion in our measurements, but a condition shaping structure itself, the question changes. We are no longer asking whether we live inside an unusual region of the universe. We are asking what it means to exist inside one. That question leads directly to the future. Because voids do not remain as they are, they grow. And they grow for a reason tied to one of the most relentless forces in physics. Dark energy does not merely accelerate cosmic expansion in general. In underdense regions where gravity offers less resistance, its influence may become even more dominant. Matter continues draining outward. Filaments sharpen. Dense regions become denser. Empty regions become emptier. The universe does not smooth itself over time. it exaggerates its contrasts. This means the cosmic web we observe today may not be a stable architecture, but a transitional phase. A temporary structure suspended between a denser past and a far emptier future. And if that is true, then the ultimate fate of the universe may not simply be expansion. It may be void domination. This is one of the strangest implications of modern cosmology. In the unimaginably distant future, galaxies not gravitationally bound to one another will recede beyond causal contact. Not merely far away, unreachable. Light emitted from them will never arrive. Not because it travels too slowly through static space, but because space itself expands faster than the light can cross. And as this continues, every large structure outside a local gravitational island disappears from view. Not physically destroyed, observationally erased. Future observers may inhabit a universe where the larger cosmos has become invisible. And this creates one of the most profound reversals in science. We happen to live at a rare moment when the universe is still legible. The cosmic microwave background is detectable. Distant galaxies are visible. Expansion can be measured. The Big Bang can be inferred. But billions or trillions of years from now, much of that evidence may be gone. A civilization arising then, even with advanced science, may have no observational access to the larger universe. Its sky may contain only its local galaxy group, no expanding cosmos, no ancient background radiation, no evidence the universe had a beginning at all. It may conclude reality is static, finite, isolated, and entirely misread the truth. That possibility is astonishing because it implies cosmological knowledge may depend not only on intelligence but on timing. Some epochs permit discovery, others may conceal it. And suddenly, the KBC void acquires a different kind of significance. Not merely as a local anomaly, but as a preview. A glimpse of what increasing cosmic isolation looks like. A window into the universe's long future. But the consequences do not stop at observation. They reach into the possibility of life itself. Because if cosmic environments shape structure, they may also shape habitability. Dense regions are violent. Galaxies interact constantly. Supernova rates can be higher. Gamma ray bursts may be more frequent. Massive black holes can disturb surrounding systems. There is abundance there, but also instability. Voids may offer something different. Quiet, fewer catastrophic interruptions, longer periods of galactic calm, potentially more stable conditions for complex life. At first, this sounds almost paradoxical. Could emptiness be favorable to life? Could isolation be protective? It is not impossible. Some researchers have quietly explored whether galaxies in quieter environments may offer advantages for long biological timescales. But the paradox cuts both ways. Void galaxies often have lower metallicity, fewer heavy elements, potentially fewer rocky planets, fewer raw ingredients for chemistry like ours. Stability may come at the cost of resources. And once again, the void refuses to simplify. It offers possibility and imposes limits. And this leads to a question even stranger than whether voids affect cosmology. Could they affect where intelligent observers are likely to arise? If so, then the fact we find ourselves inside a possible void may not be random. It may be related to the very conditions that made observation possible. That thought edges toward dangerous territory because it touches anthropic reasoning. The idea that what we observe about the universe may be partly conditioned by the fact we exist to observe it. Most physicists treat such reasoning cautiously, sometimes skeptically. But here it returns naturally. If void environments influence habitability, and habitability influences where observers appear, then perhaps our location is not merely an anomaly to explain. It may be part of the explanation. And yet, even this may be too small a frame. Because the deeper existential question is not whether voids shape where civilizations emerge, but whether civilizations inside voids can ever fully understand the universe. Think about the possibility. A civilization deep in a cosmic desert with few nearby galaxies, biased expansion measurements, perhaps distorted local structure. Would it infer the correct cosmology? Or would its location systematically mislead it? And if that possibility exists for them, why not for us? This is where the story turns inward. Because the KBC void began as a question about cosmic structure, but it now threatens something much deeper: epistemology itself, the limits of what observers can know from inside a biased environment. We tend to assume science gradually escapes local perspective, that better instruments erase parochial error, that observation converges toward reality. But what if some biases are structural, embedded in the very position from which observation occurs? Then ignorance may not come from lack of intelligence, but from vantage point. And that possibility is difficult to dismiss once one final thought emerges. The future of voids is not simply increasing emptiness. It is increasing isolation between all islands of matter. Everything not bound drifts apart. Galaxies vanish beyond horizons. Clusters disappear. Eventually, even neighboring groups are lost. The cosmic web thins into loneliness. And in that dark future, the universe may become a collection of isolated observers, each trapped inside local reality, unable to verify the larger whole. Not because truth vanished, but because access to it did. And if that is where cosmic evolution leads, then perhaps the deeper question is not whether the universe ends in darkness, but whether knowledge itself becomes impossible before the darkness arrives. And if knowledge can erode with cosmic time, then one final question begins to emerge. What if our greatest cosmological problem is not that we live inside a void, but that we may still be underestimating how much our position has already shaped everything we believe to be true? The deeper implication is not that we live in a strange region, but that our most trusted assumptions may have been calibrated inside a distortion we barely recognized. For more than a century, cosmology has relied on a principle so foundational it is almost invisible: that no location in the universe should be special. But the KBC void forces an uncomfortable revision. What if average was never something we had direct access to? What if every measurement of expansion, structure, even cosmic age has been interpreted through a local environment whose influence runs deeper than expected? That question does not merely challenge one parameter. It challenges the meaning of observation itself. Because if observers inside different cosmic environments infer different universes from equally valid measurements, then cosmology becomes partly a science of perspective. This leads to a deeper tension. Science seeks universal laws, but every law is extracted from a vantage point. We assume those vantage points converge, but large voids raise the possibility that convergence may be slower, messier, and more conditional than our models assume. A civilization inside a rich galaxy cluster might infer a universe dominated by gravitational structure. A civilization in a deeper void might infer stronger expansion, weaker clustering, perhaps even different effective laws. Both could be internally consistent, both could be wrong in subtle ways. The unsettling possibility is that the universe may reveal different partial truths depending on where intelligence emerges to measure it. This is where the KBC void stops being a cosmological anomaly and becomes something almost philosophical. It transforms the old Copernican question. We once asked whether Earth occupies a privileged place in space, then whether the Milky Way is special, then whether humanity sits at any meaningful center at all. But now the question becomes stranger. Not whether we are central, but whether our local cosmic context systematically shapes what reality looks like to us. In other words, whether objectivity itself has a horizon. There is a practical version of this question already unfolding. Future surveys will map galaxies far beyond the scale where the KBC void could influence measurements. The Dark Energy Spectroscopic Instrument, Euclid, and next-generation observatories may reveal whether the Hubble tension fades when viewed from sufficiently large scales, or whether it survives, pointing beyond local structure toward new physics. If the tension disappears, then the void may be a giant calibration error built into modern cosmology. If it remains, then dark energy, gravity, or the early universe may be more complicated than the standard model allows. Either outcome changes the foundations. But even if the measurements settle the tension, a larger mystery remains. Why should structures this large exist at all? Why should the universe generate billion light-year voids, superclusters pulling entire regions through space, bulk flows extending far beyond theoretical comfort? These are not minor wrinkles. They suggest that cosmic structure may still contain emergent behavior not captured by our current equations. We may understand the ingredients of the universe while still misunderstanding how those ingredients self-organize across the larger scales. And there is an irony hidden inside that possibility. Voids look like absence, but scientifically, absence has become information. It is the missing matter, the missing galaxies, the deficit itself that is forcing revisions. The emptiest regions of the universe may be where cosmology learns the most about itself. That inversion matters, because again and again in science, progress has emerged not from what fit theory, but from what refused to fit. Mercury's orbit led to relativity. Quantum anomalies led to modern physics. Perhaps cosmic emptiness is playing the same role now. And yet, there is still the question of observers. If intelligent life arises elsewhere, inside other voids, perhaps they too confront expansion rates that do not agree. Skies shaped by local underdensities, cosmologies built on incomplete vantage points. Perhaps the search for extraterrestrial intelligence has overlooked something profound. That other civilizations may not simply possess different technologies, but different inferred universes. Their astronomy could disagree with ours, not because one is wrong, but because cosmic geography enters into knowledge itself. If that sounds abstract, consider what it implies. Two civilizations, separated by billions of light years, might exchange data one day and discover their constants do not match. Their measured expansion histories differ. Their models of gravity diverge. At first, each assumes the other made errors. But what if both are seeing legitimate local distortions embedded inside a larger structure neither fully grasped? Then the act of comparing cosmologies becomes a way of mapping reality beyond any single observer's horizon. Knowledge would become collaborative at a cosmic scale. And perhaps that is the deeper lesson hidden inside the void. Not that we are trapped in a misleading region, but that understanding may always require stepping conceptually beyond the limits of local experience. Science has always done this. It moved beyond Earth to understand the solar system, beyond the galaxy to understand cosmology. Perhaps now it must move beyond the assumption that one location's measurements automatically define universal truth. But even that may be too simple, because there is another possibility rarely stated openly, that the KBC void is not an exception, not a flaw in the model, not evidence against the cosmological principle, but a hint that large-scale structure possesses patterns we have not recognized because our surveys are still too young. Maybe we are mistaking immaturity of data for crisis. Or maybe we are standing at the edge of a deeper rupture in fundamental physics. At present, there is no final answer. The void may resolve into a statistical fluctuation. It may help solve the Hubble tension. It may push modified gravity from fringe idea to necessity. It may fade as better measurements accumulate. Or it may become the opening clue in a revision of cosmology as profound as the shift from Newton to Einstein. And that is where the story remains unfinished. Because every major question opened by the void still hangs unresolved. Is dark energy truly constant? Or does emptiness reveal where it changes? Are bulk flows signs of hidden structure? Or evidence gravity behaves differently across vast scales? Is our estimate of cosmic age secure? Or balanced delicately on assumptions now under strain? Is our location merely unusual or epistemologically significant? And perhaps the strangest possibility of all is that the universe has not been hiding this from us, only that we have been trying to understand the whole from inside a whole.